welcome everyone. Now we are heading toward the second lecture of Kubjas. Over to you, Kaie.
Thank you. So today we will talk about geometric description of non-negative rank. And in particular, we will talk about cones and polytopes. So there is, we have already seen cones and polytopes in the last 2 days in Dr. Lin's lecture and Dr. Sarah's lectures. So it will be in the same direction. And although we're all familiar with cones and polytopes already, so I want to give the first definition to make, to fix the notation. So I will be talking about finitely generated cones, although yesterday we saw by the Minkowski-Weil theorem that these are exactly the same as polyhedral cones, but just to make sure that we use the same notation. So given a matrix A of size m times n with real entries, then, as I said, for me, cone A will be the finitely generated cone generated by the columns of A. So, and more formally, so it consists of all the elements x, such that x is equal to a times y for some y in Rn. And y needs to have non-negative coefficients. So this is what it means. It's finitely generated cone, and x lives in Rn. Okay, and so let's also quickly recall a few examples. So if we consider the matrix with entries 0, 1, 2 in the first row and 1, 1, 1 in the second row, then the cone generated by A, so the three columns are, give these elements over here, and then the cone generated by this matrix is this cone over here. And all elements of cone of A are conic combinations of the columns of A. So every point here is a conic combination. So this means it's a linear combination where the coefficients are non-negative. And so let me recall the dimension, although we also saw this definition. So the dimension of cone A is the dimension of the linear span of the columns of A. And in other words, the linear span is also equal to the rank of A. And first, we will give a characterization of non-negative rank using finitely generated cones. So this is like, let's say, more natural way to give this characterization. And then we will give it using polytopes. There's a question. This picture over here. Okay, so how we get it is we look at this 3 points that are the columns of A. And then basically, we also consider the point 0. And then we take this supporting rays. So in this case, this would be the supporting rays. So it's easy to see that the supporting rays need to be in the cone because in this case, the y is the vector where exactly one coordinate is non-zero. And then, also everything between the rays have to be inside. And now for that, we consider vectors y where we have more than one non-zero coefficient. So maybe, so since there was this question, what would be the cone of A for this matrix?
Half spaces.
So I heard the correct answer, so it would be the positive orthant or non-negative orthant in R3.
Yeah.
Right, so now the 3 elements are the 3 unit vectors. So these are the like rays of this cone. And then we have to take also like all the convex combinations of rays. Okay, so this was a reminder about cones. So now let's connect it to its non-negative factorizations. So let us consider NMF. Let's recall that was non-negative matrix factorization of a matrix X. And this is the non-negative factorization, meaning that all the entries of this matrices have to be non-negative. And recall that we also had, if we consider a column of X. So this notation means I'm considering the J column of X. So this column means that we consider all the rows and the column is fixed to be J. And so this is something that I also wrote down yesterday, that if you have this factorization, then we also get that the J column of X is equal to W times the J column of H. So okay. And also because we talk about non-negative factorizations, then W is, has non-negative entries and H has non-negative entries as well. Okay. Does anyone see already like which cone we might be talking about? So you don't have to see, I'm going to write it down, but if you compare the definition here and what I just wrote down over here, like, does anyone see any cones?
Yes.
So we don't require positive definiteness yet. So let's look at this over here. We had that we are considering all the points x, where x is equal to a times y, where y is non-negative. So A is a matrix and y is a vector and x is a vector.
So cone of W.
Cone of W, exactly, because this is vectors, right? These are vectors and these vectors are non-negative, exactly as in the definition of finitely generated cone. And then W is our matrix. So hence, these columns are in the cone of W. And so this is the cone part. So that comes from what I wrote down here. But furthermore, we have something more here. We also have that this cone is in fact included in the non-negative ordinate. And the reason for that we have a cone comes from the fact that H is non-negative. Right, so because in the cone definition, we need that these vectors over here have non-negative entries. But then that this cone of W is included in the non-negative ordinate comes from this part over here. So this says that all the rays, so the columns of W, or the rays are included in the columns of W. This says that they are all in the non-negative ordinate, and this means also the cone has to be in the non-negative ordinate. So for all J. And equivalently, let's write it in terms of cones. Cone of X is contained in cone of W, is contained in the non-negative ordinate. This will be an exercise. This first containment, it's an easy exercise using the definition of cone. I think it's good if we think about it more tomorrow. And also the non-negative ordinate is a cone. So Dr. Dinle mentioned it yesterday, but we really have inclusion of 3 different cones. Okay, and this is called a nested cones problem.
What is the role of H?
Well, the role of H is that it gives them coefficients like the conic coefficients in the conic combination. So
I mean, the same relation can be said for cone of H.
That's true. We could do it symmetrically, that we consider the rows of X, and then we could consider the cone of the rows of H. And then we get very similar. This is true. So we do it with W because I mean this is a choice we make, but you're completely correct. We could do it symmetrically for H, but then we have to consider the rows.
So when we talk about H, we will consider the cone of rows of H.
Exactly. And one way how to see it, we could transpose everything here. Then we could get X transposed is equal to H transposed W transposed. And then we can think, you know, if you think of the columns of the X transpose, they are rows of X, and columns of H transpose are rows of H. So everything, what is columns here becomes rows. So maybe using transpositions is the easiest way to think of it. This is a nested cones problem, and let me write down once more what is a nested cones problem. So given two cones nested in each other, and nested in this case means one is contained in the other. So namely, cone of X is contained in the non-negative ordinate. Find a cone nested between them. Namely the cone of W. And yesterday, after the lecture, there was a question. So if we are given a matrix, how to like determine if it has rank non-negative rank R, or like how to find the size non-negative rank R question. So one way to do it is to answer this nested cones question. So we are given, so X we know, and we know M we know. So these are the two things that are given. And we want to know, can we find this cone W that's in between these two cones? So this is a geometric characterization of this question. Okay, and let me write it in a different way once more. So because right now I said it's equivalent to finding a cone W, or equivalently, it's we can find some vectors in Rm. So NMF is equivalent to the nested cones problem of finding R vectors. It will give us the columns of W. In the non-negative ordinate. Such that cone of W contains cone of X. So basically, I'm saying the same thing that I said here, but I took it even more, you know, writing it in more in detail. So let's do an example. So geometric illustration of what we just talked about. So we are given our matrix X, and let's do a very simple case because, yeah, I don't know how to draw higher dimensional cases where X has 2 rows. So let this be columns of X. Okay, so then cone of X is this cone over here, right? Then we also have the, otherwise the picture gets very complicated. We also have the cone of, or the non-negative orthant. And let's say in this case, we want to know if this matrix is non-negative rank 2. If you remember the properties from yesterday, then we actually know that it has non-negative rank 2 because it has rank 2. It has two rows, but let's say we don't know it for a moment. Then, for example, we could take these two vectors over here. Let's say this will be the first column of W. This will be the second column of W. And then this gives us a cone that's between cone of X and the non-negative orthant. Are there any questions so far? Because we will continue with the same topic, but so far it was cones, and now we will go on with polytopes. So in some sense, it's going to get even more complicated. So we will give a related geometric description using convex polytopes. And it's interesting because this cone's description is more natural, like it comes directly from the definition. But then, in my opinion, people usually actually work with the polytopes description. And one reason is that the polytopes description is somehow easier to visualize, but of course that doesn't really help if you're proving theorems, but nevertheless, somehow the polytopes description is more common. And maybe one more thing that you might wonder, like, why are we giving this geometric description? It turns out this is really one of the main tools that people use when they're proving anything about non-negative factorizations and rank. So somehow the tools in convex geometry are already there, or that one can use. So that's one of the reasons. So it's really very common in this literature. Okay. So as for cones, I assume that you already know this, but just to fix the notation, let me recall what is a polytop. So given a matrix A, so in today's lecture, the polytop is the convex hull of A. So yesterday we saw that this is equivalent. We could also define a polytop using hyperplanes or half spaces. We use convex hull. So now I'm writing down almost the same thing as I wrote for cones, but there is like one addition. So as before, we require that y is non-negative. So this would now us give a cone. But furthermore, we require that the sum of coordinates of y is 1. So this is what it means, convex hull. And all the elements of convex hull of A are convex combinations of columns of A. So this means it's linear combinations where also these two conditions are satisfied, that y is non-negative and the sum of coordinates of y is equal to 1. And then maybe one more thing that I want to recall about polytopes. We talked about faces yesterday. We didn't talk, but in last talk. So the vertices of the convex hull of A are the columns of A that are not contained in the convex hull of any other columns of A. Okay, so let's also quickly do an example. So let's consider this matrix 1, 0, 1, 1, 0, 1, 2, 2. Then the convex hull of it is, so let's first mark the 4 columns. So the convex hull is the triangle with 3 vertices, and the vertices are the columns, the first column, the second, sorry, not the second one, the third one, and the fourth one. So vertices are contained in the columns of A, but not every column of A needs to be a vertex. So in this case, 1, 1 is in the interior of this convex polytop. And let's also recall, also saw it yesterday, but because it's very important. And in the polytopes world, this is like what corresponds to the non-negative orthant. So we saw that a non-negative orthant was cone. So the unit simplex is the polytop that will correspond to the non-negative orthant. denoted by delta R minus 1. So although it's in the R dimensional space, the dimension will be R minus 1. So that's why the index is R minus 1. So it consists of all the elements in R to the R such that all coordinates of X are non-negative and the sum of coordinates of X is 1. Or can anyone tell me if we use the notation that we just introduced as a convex hull, what should I write here?
Identity matrix.
Yeah, so the identity matrix IR, right? So this is R times R identity matrix. And note what I did. This is the description that we used now as convex hull. And this is now the descriptions that we saw yesterday using half planes and half spaces. And maybe another quick question to make sure that everyone's awake by now. So what are the vertices of delta R minus y? Delta R minus 1.
I have a question before that.
Yes.
So the condition to be in that unit simplex is that X has to be non-negative component-wise, and the sum should be 1.
Exactly.
Why does that identity? It could be, it includes even X can be a probability vector also.
Exactly. So it's also known as the probability simplex. So depending in which community you work, if you work in discrete geometry, you maybe know it as a unit simplex. If you work in, let's say, in statistics or probability, you know it as a probability simplex.
Yes, I have a different definition that unit simplex is basically a simplex from standard basis, and probability simplex is the one that comes from this one. So maybe.
Yeah, so you almost gave them. Now, can you give an answer to this question?
The points on the intercepts of the unit intercepts of the x's.
Exactly. So it will be the unit vectors. Yeah. So are the unit vectors E1 to ER? Okay. So much of recalling things. So now let's go back to the non-negative factorizations. Okay, so I'm going to begin the next. So now we will learn how to modify non-negative matrices, and we learn like modifications that doesn't change non-negative rank. And we learned this modification so that we could give this this description using polytopes. So given a matrix A with non-zero columns, let DA be the matrix, be the diagonal matrix actually. Whose entries are so they're equal to 1 over the column sum if you have the diagonal entries and 0 otherwise. So what I have written here, it's the 1 norm of ith column of A. And because A has non-negative, okay, I didn't say that, but let's say in our case, the matrices will have non-negative entries, then this is nothing else than the sum of entries in the ith column of A. Okay. And what we will do, we will multiply our matrix A with this diagonal matrix DA. So define theta A to be A times DA. And can anyone tell me what property this matrix theta A has?
It's less than, it's bounded less than 1. Entries are less than 1. Utilize every.
That's also true. Yeah, so it's scaled such that each column of theta A sums to 1, right? Because what we do, we take the matrix A and we multiply it with a diagonal matrix where the diagonal entries are 1 over the column sum of A. Okay. It's also called by normalizing or scaling. Let's see an example. So if you consider the same matrix as before, then theta A will be the matrix. So we check if the columns sum to 1, and if they don't, we scale. And an intuition, what we are doing. So we had this cone before, like, I don't know if I have the drawing. Luckily I have the drawing. But I think I want this picture for now. So remember these points were the columns of X. So basically what we are doing, we are scaling the columns of X for all them to be on this line segment, right? So everything maps to the, so let's say this one goes here, this one goes here, this one goes here, etc. So we map everything to this line segment. And actually they will be all in this unit simplex. So that's why I said the unit simplex will play the role of the non-negative orthant. So, and the reason for this is so that we can talk about polytopes, and polytopes are much easier to visualize than cones. And I'm going to skip a little bit of the details here, but it's actually not so difficult. So if anyone is interested, we can talk about it today during the discussion. So one can show that if the columns of X and W don't contain any zero columns, zero vectors, to stop now at the most interesting part, but you can think what might come here or what might come next.
Very stupid question, and maybe I'm wrong. Shouldn't D be on the left of A because you're scaling the columns?
No, because if you think, I hope I'm correct, actually. But
because the first row of A will multiply by the first column of DA, which only has the entry that, so you're row normalizing on the right side, and you want to do column normalization, and DA should be on the left.
So let's try it on a small matrix to make sure that we're correct. So, and let's say here's the theta1, theta2, etc. So let's see, what do we get in the first column? So, and here is all zeros, right? So we get A11.
So the whole row gets scaled by theta1, which should not be the case.
Well,
no, so first row for the first row in A gets multiplied by the first column in DA.
Yes, but this is all zeros. So this entry will be A11 theta1 because here everything is zero, right?
Oh, okay, sorry.
And then one. But this is, I always mix up on what side we have to multiply. So, you know, this is a very common thing. And also like whether the sums, rows or columns sum to one, you know, like usually.
And I think I also, it was a childish question because if it's a diagonal matrix, then left and right doesn't matter. Left also, that's a mistake on my part. So if it's a diagonal matrix, left multiplication, right multiplication, they don't matter.
They do, because if I would be multiplying from the left, then I would be scaling the rows. Okay. So it does matter whether we scale if we want to scale the columns, we multiply from the right. If we want to scale the rows, we multiply from the left. But I agree, I'm confused all the time. So, but for the lecture, you know, I try to make sure that I get it correct for once. Okay, so we stop there. If X and W don't contain any zero vectors as columns, then one can show that our nested cones problem, like this inclusion of cones, is equivalent to the following nested polytopes problem, where we replace X by theta x. So just using the operation that we introduced where we scale the columns of x. And here comes the unit simplex. And this is not very hard, but right now I don't have the time to show this this equivalent. So but let's say the proof is basically some manipulation in linear algebra with like multiplying with some of this D matrices and unique vectors and one more thing. So I've been in several places saying that one can show that if the columns of X and W do not contain zero vectors. So this is actually not a restriction. So if our matrix X contains a zero vector, we can just take it out because it doesn't influence the non-negative factorizations. Okay, then let's write down a very important theorem by Kohan and Rotblum. And it appeared in 1993 in linear algebra and its applications. And as I said, let's say non-negative factorizations appeared already in the 60s in applications. But to my knowledge, this is one of the first like theoretical papers on studying non-negative factorizations. And many of all these polytopes things is like in this paper. And this theorem says that computing the non-negative matrix factorization is equivalent to finding R vertices in the n-1 dimensional unit simplex such that their convex hull contains the convex hull of theta x. So basically, it's already what I wrote here. Okay, let's do a picture. And I'm not sure if you will be actually able to understand this picture. We are in R3. So this what I draw is the unit simplex. So the delta 2. So it lives in R3, but it's two-dimensional. It's a triangle. And let's say the convex hull of X is a quadrangle. And this means we're looking for 3 vertices that contains a quadrangle. But of course, this example is not so interesting because we could just take the 3 vertices to be these vertices. The problem is that I can't right now draw higher dimensional examples. But actually I could, and we will in the 4th lecture. And the reason for this is that we are drawing some redundant information, right? We are drawing these pictures in 3-dimensional space, but everything here is 2-dimensional, right? And this is because we're in this unit simplex. The last coordinate we can already get from the first n-1 coordinates because we need that the m coordinates sum to 1. Okay. Maybe let me just write down this remark because I think it's quite important. And then we finish today's lecture with a proof idea for one of the properties yesterday. And I'm saying proof idea because I'm skipping some details, because if one would want to give rigorous proof, let's say, we would have to spend a couple more lectures, in detail, actually proving everything that I've stated. So, remark. Point. Delta m minus 1 contains redundant information . So since the sum of xi's is equal to 1 for x in the unit simplex, we have that xi is equal to 1 minus sum of all the other coordinates. So j not equal to I for all I. So we could really leave out one of the coordinates and we have full information. Okay, so and to finish this lecture, let's prove one of the properties, the only property that's not trivial from yesterday. So if X is a non-negative matrix with rank of X equals to 2, then non-negative rank of X equals rank of X. We also had the same is true if the rank is equal to 0 or 1, but these cases are, like, let's say, easy to prove. And this is one that's not so easy. At least not knowing this geometric characterization.
How that particular remark that X cannot be the vertex of the simplex, or would be a point inside that simplex?
It doesn't matter if you take anything in the unit simplex. So if it's vertex, so then either if I take a projection, it has all zeros, and then I know that the missing coordinate needs to be 1. Or it has zeros and 1, 1, then I know that the missing coordinate needs to be 0. So it can be also a vertex.
It can be.
Yeah, so anything. And actually, so I wrote here for the unit simplex because we work in the non-negative orthogon, but the same is true really for anything on the plane, hyperplane containing the unit simplex. Okay. So, and for the first sentence, you have to believe me. So it can be shown in the case when rank of X is 2, that actually this polytop convex hull of theta X is a line segment. So, and this I'm not proving, and it's not trivial. Let's say it's not very hard, but it's not immediate. But actually, there is a more general statement that if the rank of matrix X is K, then this convex hull of theta X is K minus 1 dimensional. So, so this is true in general. And if the rank, in our case, rank is 2, so 2 minus 1 is 1. So 1 dimensional polytop is a line segment. Okay. And then the vertices of convex hull of theta X are 2 columns of theta X. Remember, we talked about it that the vertices are always contained in the columns of the matrix, but not every column is a vertex, right? And thus we can take theta W to be equal to these columns of theta X. I just realized maybe I didn't write it in the most precise way. What I mean, delta W has 2 columns, and these are precisely these 2 columns that give the vertices of theta X. Okay. And let me finish the proof here. So I'm going directly down. So hence, rank of non-negative rank of X is less or equal than 2, because we have found this W or delta W 2 vertices. Okay. On the other hand, non-negative rank is greater than rank. So this was also one of the properties from yesterday, but this I'm claiming is easy to prove. So we have that from this geometric characterization, non-negative rank is less or equal than 2. From here, we get it's greater or equal than 2. Hence, non-negative rank of X is equal to 2. And this completes the proof. And actually one can, one can prove this also using linear algebra, but it's much messier. I'm skipping lots of details here, but let's say once we have this geometric picture, the proof becomes much easier than, doing all the manipulations with the matrices. Okay, so I will stop here. So tomorrow we will talk about something completely different. So tomorrow we will not talk about non-negative rank. So we will do preparations for the 4th lecture. We'll talk about real algebraic geometry. We'll recall some things from about varieties. And then in the last lecture on Friday, we will combine everything. We will combine what we learned today, and we will combine what we learn tomorrow, and then we'll talk about real algebraic geometry and polyhedral geometry together. Okay. So that's all for today.